starting to stream on YouTube, and anyone who does not wish to be seen in the videos or heard should mute themselves and turn off their camera. But yeah, so we are now live on YouTube. We will start a cloud recording as well soon. So yeah, this seems to be working. If someone could also verify the stream is live.
Yep, I can see a live stream.
Okay, good. Yeah, so let's also start a cloud recording. Okay, so welcome everyone to the 2021 edition of the online Open Probability School. As most of you are aware, we started this last year when the CRM PIMS summer school and other schools were cancelled due to the pandemic, and unfortunately travel is still highly constrained, problematic, and so we are doing this again. Perhaps for the last time, but we'll see. So we have a pretty good lineup of courses. Most weeks we'll have a single course. The schedule is on the OOPS website, which can easily be found. And this week, exceptionally, we have two courses. We have Pierre Tarres about to begin, and Asaf Nachmias will speak in just 2 hours. So we will have a roughly 1 hour break. So if you have any questions in the meanwhile, as usual, you can ask in the chat, or you can unmute and just ask. So hopefully this will go smoothly. And of course, we can stop the recording afterwards and have time for questions as well. So as noted before, so this is being recorded and streamed live on YouTube, and the videos will be available afterwards. So if you do not wish to appear in the recordings, then make sure your camera is off and your mic is muted. And with that out of the way, I think we can get started with the first course for this summer. We are happy to have with us Pierre Tarres from NYU Shanghai, but currently in France, who will tell us about star edge reinforced random walks and other related things. So Pierre, the floor is yours.
Okay, thank you very much for the introduction, Omer. What I will talk about is the star edge reinforced random walk. So it's a non-reversible generalization of the edge reinforced random walk. Basically, I will talk about a few processes. So all are reinforced processes. So what do I mean by reinforced random walk? So how do I define it? So I think the best way to define it is these are the processes I've been working on for 20 years. But so basically, there are processes which are reinforced by their paths. So they keep a memory of, let's say, the number of crossings of edges they have done on a discrete graph, or the numbers of sites that have been visited. and the more sides have been, let's say, edges have been crossed, the more they are likely to come back to those edges. But and I will see another version, which is a vertex reinforced jump process, where I jump from one side to the other at a rate which is proportional to the local time at that site. So, but all these processes have in common the fact that they are exchangeable. So, so I will discuss what I mean by that. And because they are exchangeable, they can be seen as random walk in random environment. So, so basically, there are mixtures of Markov chains. And that structure enables us to do Bayesian statistics. And actually, so the way I will introduce the star edge reinforced random walk is through Bayesian statistics for Markov chains. But in this first lecture, I will focus on that link between edge reinforced random walk and Bayesian statistics. And I will actually show that this link enables us to guess what the limit measure is. So the first case of exchangeability I will take is the so-called Pólya urn. And we will do the computation of the limit law. And then we will go on to the edge reinforced random walk. So, so first, we will basically in the first half, we will study that Pólya urn. We will introduce the notion of exchangeability, and then a statistical view we can have on that. We will find the limit law, and then the edge reinforced random walk. So the notion of partial exchangeability, how you can show that it's partially exchangeable, the statistical view, and how to find the limit measure. So the full computation of the limit measure will finish by the beginning of next lecture. So first, the Pólya urn. So the Pólya urn was introduced by Eggenberger and Pólya. And so in a paper in 1923. And so über die Statistik für Verkettete So the statistics of linked behavior. So the idea that they had is that, okay, you come to a doctor and he notices that you have, you are ill. Okay, you have a certain kind of illness. So let's say you have a cold, or today it will be you have COVID. And then a next patient comes and he notices again that so he has the same disease. Then the third one comes and he doesn't have the disease. And then the question is how you guess what percentage of the population is sick. So it's formulated like that, although no results of Bayesian statistics are really given. So the way they look at that kind of evolution in time of the number of let's say sick people and healthy people. Let's say healthy would be green and sick would be red. So that you have an urn with balls of two colors, so a green color and a red color. And you start initially with A, respectively B balls of green and red color. So let me note here that A and B in the definitions we will take do not need to be integers. So the definition will hold on even for any positive number. And then, so we will consider two stochastic processes, so Gn and Rn, which are the numbers of green and red balls until the nth row. We start with G0 equal to R0 equal to 0. So they are the number of balls which are added until that row. And then so basically at each time step, you so you have these balls of two colors. You pick a ball at random, and if you pick a ball at random, the probability is that you pick a green ball is proportional to the number of green balls. So at time n, it will be A plus Gn divided by the sum of number of green balls and red balls. So A plus Gn plus B plus Rn. So let's call that quantity alpha n. So you take that ball, you look at the color of this ball, you put it back together with a ball of the same color. So is that definition clear to everybody, or do you have a question? So again, you at each time step you pick a ball at random and you put it back together with a ball of the same color. So now why is this process particularly fundamental? Because it satisfies a property which is exchangeability. So roughly speaking, exchangeability means that the probability to do a certain group of choices, so let's say that your trajectory G0 up to Gn be something, does not depend on the the precise trajectory you did, but only on the numbers of green balls you will have added at time n. So in other words, it's stable by permutation. So if you take random process xi, taking values in 0, 1, so either 0 or 1, so in order to simplify, you will call x exchangeable if for any permutations on n elements, the law of x sigma of I, so x sigma of 1, etc., x sigma of n is the law of xi, x1 up to xn. And the Finetti proved that if a process is exchangeable, then there is a random variable alpha, strictly so alpha between 0 and 1, and in general you can easily prove that it will be strictly between 0 and 1 if the process is not trivial, and alpha will be the limit of 1 over n multiplied by sum from 1 to n of xi. So in the case of Pólya earn here, that would be xi would be whether you pick a green ball at time I. So that proportion 1 over n multiplied by the sum of xi would be the proportion of green balls. So the proportion of green balls which converge to alpha. So now an even more interesting part is that conditionally on alpha, you have a very simple structure. So the law of xi is conditionally on alpha is an IID sequence of Bernoulli random variables with success probability alpha. So which means that conditionally on that limit proportion of green balls, you would pick from the beginning, from the first time. So this is not an asymptotic theorem. This is really a theorem which holds from time 0, time 1. So conditionally on alpha, you would pick a green ball with probability alpha at each time step, independently of the other time steps. So again, don't hesitate to interrupt me and to correct me if you find typos. So I'm sure you will find some during the lectures. So now, why is the Pólya earn exchangeable? So this is an easy calculation, so which I encourage you to do. But so we are going to prove that it's exchangeable, but also a little bit more. So because we want to prepare that computation of the limit law, so we are going to write the formula for that probability. So let's first introduce some notation. So we define P AB, the law of the Pólya urn starting from A respectively B green respectively red colors, both of green and red colors. And so we define A comma n in parentheses as the product of A, etc., up to A plus n minus 1. So you can note that this is also the gamma function of A plus n divided by gamma of A. And we also define C of AB as gamma of A, gamma of B divided by gamma of A plus B. So now lemma, which so you can do as an exercise. So you take a Pólya urn, and so you set xn. So again, xn is the fact that you have a success at time n. So in other words, that you chose a green ball at time n. So it's gn minus 1. Then xn is exchangeable. And the formula for the probability of a path xi being equal to epsilon I. So it only depends on the number of green balls you will have taken at time n. So P, the sum of epsilon I from 1 to n. So this is the number of green balls. Q is the number of red balls. And this is the formula is C of A plus P, B plus Q over C of AB. So how to prove that? So it's rather simple. So basically, when you compute the probability of such a path, so you first note that, so in this formula here, at each time step, the number of balls increases by 1. So therefore, at time n, the total number of balls is equal to n. So the denominator here at time n would be A plus B plus n. So therefore, on the denominator, you will have something like A plus B multiplied by A plus B plus 1, etc., multiplied by A plus B plus n. So now on the numerator, you have similar structure. So every time you choose a green ball, so let's say the first time you choose a green ball, you get A on the numerator. But the second time you get A plus 1, up to the last time you choose a green ball, which will be A plus P minus 1. So here actually you can prove that, so before writing that formula the way I wrote it, you can prove that the formula is also, the numerator would be A comma P multiplied by B comma Q divided by A plus B comma N, which you can rewrite this way. So it's an easy computation. So, okay, so now let's take a statistical view. So given a sequence of IID Bernoulli random variables with an unknown random success probability alpha, how can we estimate alpha? So that was kind of the spirit of the question of Eggenberger and Pólya. So you have a law with a certain of Bernoulli random variable with a certain success probability. You don't know that success probability alpha. How can you deduce it? So a simple way would be simply to count the proportion. But here, so the Bayesian statistics approach is say, okay, let's assume you have you choose a prior distribution on that random variable alpha. And if you choose that prior distribution, and then now you know that so you will have added some let's say at time n you will have added P green balls and Q red balls, then your prior distribution will be changed accordingly. So basically, and so you will see that somehow your posterior distribution, if the time n is large, it will be kind of centered around the mean. So the proportion of green balls in the so here, we let L of AB be the law of the random variable alpha under so that PAB, which is the law of the Pólya urn, starting from A green balls and B red balls. And if the prior on alpha is L of AB, then the law of the successes at time n is equal to the law of Gn minus 1. So how to prove that is just looking at that exchangeability. So consequence of exchangeability so basically, so you write, so in other words, you write, so you somehow the Pólya urn is an annealed law, and then once you know the alpha, so you know the alpha is distributed with respect to that law L of AB, but once you know the alpha, simply you have Bernoulli triads. So that's why you can write this equality. So, okay, so any question again? So is everything clear? So now a very simple remark is that if the prior on alpha is L of AB, then the posterior distribution after P successes and Q failures is L of A plus P, B plus Q. So why? Simply because if you have done P successes and Q failures, so then that means that you will have added P green balls and Q red balls. So you will start with an urn which will have A plus P green balls and B plus Q red balls. So you know now that your distribution of alpha would be given by that. So that gives that result. So you see that, in statistical terms, that means that the prior and posterior are in the same family of probability distributions. So actually there are beta distributions, but so we are going to prove it. So I'm not writing it now, and they are called conjugate priors. So now an important notion is the notion of sufficient statistics. So informally, it means that no other statistics can be computed from the sequence of successes. No other statistics that can be computed from that sequence provides any additional information on alpha. So formally, it means that so you choose a certain statistical model, P alpha. So P alpha here is simply the Bernoulli 0,1 with success probability alpha. And now you compute the probability of a certain path of successes and failures, knowing the total number of successes. And that probability, that conditional probability, does not depend on alpha. So this is an easy computation, so which I encourage you to do as an exercise. So basically, you do this probability, so this Bernoulli 0,1 law with success probability alpha. You condition on the total number of successes is actually, so the whole sequence does not depend on alpha. It is also a minimal sufficient statistic. So it means that there is no other sufficient statistics that needs less information. Okay, so now how to compute the limit law. So the ones who have experience here may think, okay, you know, the limit law of Pólya urn, it's been known for a while. So why is he spending so much time on it? So actually it's known and there are various ways to compute it. But here I will focus on a computation which somehow only makes use of that property that the posterior distribution of alpha after peak successes and Q failures is L of A plus P, B plus Q. So, the argument is as follows. So you assume that the law of alpha under PAB has a smooth integrable density measure phi AB with respect to the Lebesgue measure on 0, 1. Now you are going to look at the probability that that your limit alpha is between x and x plus dx condition on a certain trajectory you did. So xi equal to epsilon I. So I between 1 and n. So again, you take the same notation. P is the number of successes, Q is the number of failures. And here you confront two views. So one is an ill view. So the anneal view is the Pólya urn as we defined it at the beginning, where you add balls in proportion to the number of green balls. So green balls in proportion to numbers of green balls. And the quench views, where you say, I have a certain distribution on alpha, but conditionally on alpha, between being, let's say, x, so I know that the probability of the same path would be x to the p 1 minus x to the q. So here, how do I compute? So I say that this probability, obviously, this is the probability of the intersection. So which is alpha x between x and x plus dx and the path divided by the probability of the path. So probability under AB of xi equal to epsilon I for I between 1 and n. So the denominator here, so the event on which you are conditioning, we already know its probability, the probability of that event on which you are conditioning. So this is C of A plus P, B plus Q divided by C of AB. Therefore, now you understand that part. So now let's look at the numerator. So the numerator, so the probability that alpha is in x plus dx, so this is phi AB of x dx. And so given that, so the probability is that you have P successes and Q failures. This will be x to the P 1 minus x to the Q. So conditionally on that. So therefore, you get that formula that this probability of AB, so between of alpha between x and x plus ds, knowing that path is equal to that. So now this probability here, this is also the probability again. So you know that, so that conditional probability is also the probability corresponding to having A plus P balls, green balls, and B plus Q red balls. So you can write it as the probability as the same event, but not conditioned with A plus P and B plus Q as exponents. So in other words, here we have proved that phi A plus P, B plus Q of x is equal to phi AB of x multiplied by x to the P, 1 minus x to the Q, C of AB divided by C of A plus P, B plus Q. So you can see that with that rather simple argument that the posterior distribution is L of A plus P, B plus Q, you obtain an interesting formula, which functional formula, so which relates the function phi A plus P, B plus Q to the function phi AB. Okay, so now, so I'm going to write it here a little bit differently. So you will see why in the next slide. So here's the x to the p. I will write it as the quotient of x to the a plus p and x to the a. So that you see that here you will have a quotient of somehow this quantity x to the a plus p 1 minus x to the p plus q over the c at a plus p b plus q divided by the same quantity but taken at a and b instead of a plus p and b plus q. So that kind of gives an elegant way of writing this formula, which will be helpful. So okay, so now, we have already made significant progress. So we can relate these densities by this simple formula. But how can it give us the phi of AB, which we started from? So here you need another remark, which is very simple, is that so if P and Q are very large, if you look at the, x to the p 1 minus x to the q on the right-hand side, this quantity actually has a peak around p over p plus q. So it's really concentrated around p over p plus q, and basically on the rest, it is so on the rest of the interval it's basically 0. So it's approximating a Dirac function at p over p plus q. So that's basically what we are going to prove. So now why is it useful? So actually so more precisely you can see it as a Gaussian close to a Gaussian random variables centered at p over p plus q. So actually it wouldn't be p over p plus q, it would be a plus p over a plus b plus n. So so now if the right hand side here is kind of concentrated around only one point, and it is Gaussian, then when you integrate it, you should just get the integral of that Gaussian multiplied by phi AB of p over p plus q, right? So that's what you get. But on the other hand, when you integrate, you know that the integral is 1. So if you confront those two approaches, you should get a formula for phi AB of x. So that's what we are going to do now. So let's introduce first some notation. So first, recall that n is p over p plus q. So now define beta of n. So this is a proportion of green balls, a plus p over a plus b plus n. And so let's use now Stirling's approximation, so which has nothing to do with Stirling. So gamma of z, so well, gamma is gamma function is equivalent to square root of 2 pi z to the power of z minus 1/2 multiplied by e to the minus z. So here, so I leave it to you as an exercise. So it's a little bit tedious, but it's interesting too. So I just heard that the recording stopped. So is it still working? Okay, so it's working again. So good. So okay, so now using Stirling's approximation, you get that. So after some computation, you get that. This quantity, say C of A plus B, B plus Q, when P and Q go to infinity, is equivalent to square root of 2 pi n, so n is the time, multiplied by the square root of beta n, 1 minus beta n, multiplied by a certain function eta beta of n taken to the power of n, where eta beta of x is x to the beta multiplied by 1 minus x to the beta. Yeah, I think, okay, let me, yeah, sorry. I'm just, yeah, it's 1 minus x to the 1 minus beta. Sorry, there is a typo here. So it's x to the beta multiplied by 1 minus x to the power of 1 minus beta. So now, so you can get this formula. So again, I leave it to you as an exercise. So remember that there is a session which is not recorded tomorrow. So 2 hours before the lecture, where you can come and ask me questions on how to prove those and other questions also that you are interested in. So here, what do we obtain? So let's look at the formula here. So so we have the phi. So one part here, you know, on the right hand side, the two last parts actually only depend on A and B. So they are fixed when you make B, P and Q move. And so then the first part, so we have the asymptotics of the denominator here. So C of A plus P, B plus Q. And so then you have the x to the A plus P, 1 minus x to the B plus Q, so which will give you that eta beta of n of x to the power of n. So you get that formula. So here I have put on the left the part which is not changing, so only depending on A and B, and then you multiply by that. And then, so now you have to notice that eta beta of x, so again, it is concentrated around beta. So if you take the log of eta beta of x divided by eta beta of beta, you get something which is minus x minus beta squared over 2 beta 1 minus beta plus a smaller term, smaller order term. So then you see, so that now the next idea is just to notice that the integral of the part on the right hand side, so starting from 1 over square root of 2 pi on the first display, so this integral will be almost Gaussian integral, and actually it will converge to 1. So in other terms, so we'll have that this limit here, so which is also 1, because all these phi's here are density, probability density. So this limit, which is 1, so will be equal to phi AB of x multiplied by C of AB divided by x to the A, 1 minus x to the B. So actually there is a typo here. So it should be x to the A minus 1, 1 minus x to the B minus 1. So sorry about the typo. I'm sure we'll find some more later. So and here you use the fact that so this integral here is 1. Okay, so again, so you can conclude that phi AB of x should be x to the A minus 1, 1 minus x to the B minus 1 divided by C of AB. Okay, so are there some questions at that point? Okay, so let me now start with the edge reinforced random walk. So it was introduced by Coppersmith and Diaconis, and so the story is that Percy was visiting Paris, and so he noticed that he was kind of visiting more often certain streets, and so he wanted to consider a process associated to it. And what is so what he does here is that so you take a discrete graph, so a non-oriented locally finite graph, G with vertices V, edges E. You start with initial weights AE, positive AE, E non-oriented, and the edge reinforced random walk XN on V. So it starts from so you start from a certain site I0, and so at each time step n, so you have a memory of the number of visits to crossings of edges. So Zij of n is, so Aij, which you consider by convention as the initial numbers of crossings. So Aij plus the number of crossings up to time n. And then so the conditional probability of moving from I to j will be proportional to this number of crossings of ij. So this will be Zij of n divided by the sum of those terms for k adjacent to xn, to the where you are. So now, kind of simple remark, but so important, is that here, if AE is small, you have strong reinforcement. So why? Because then, so when AE, let's say, is epsilon, very close to 0, then at the first crossing of that edge, you go from so epsilon to 1 plus epsilon. So you are under, you have a big change in comparison to AE, so the case where AE large, so which corresponds to small reinforcement. So why is this process particularly interesting? So it's because it's partially exchangeable. So what does it mean? It means that the probability of a path only depends on the starting point, of course, and the number of crossings of edges, so of non-oriented edges. It does not depend on anything else. So let me introduce that notion more formally here, so which was introduced also by Diaconis and Freedman in 1980. So you take a process yn, taking values in the vertices of a certain non-oriented locally finite graph, and you call it partially exchangeable, respectively reversibly partially exchangeable, if for any nearest neighbor path on the vertices, the probability that your process does that path only depends on its starting point, on the number of crossings of the directed edges, and in the reversible case of the undirected edges. Okay, and so and now the result that Diaconis and Freedman have is that when a process is partially exchangeable, then it's a mixture of Markov chain. So there is an underlying environment, and conditional on that environment, you have a Markov chain. And so you see that we are going to use the same structure again, so of kind of confronting the annealed and quenched version. So the theorem by Diaconis and Freedman here is that so if that process is almost surely recurrent, so which means that it comes back infinitely often to its starting site and partially exchangeable, then it's a mixture of Markov chains. So here I'm writing that the law of that process is the integral against the law of a certain environment omega, which corresponds to Markov chain with transition probability omega of ij from I to j, and condition on omega you have so this is so condition on omega you have that Markov chain, and you have a certain law d mu on so mu on omega. So if now in the reversible case, so you need an additional assumption that each edge is traversed at least once in both directions with probability 1. Then you can show that so the corresponding Markov chain will be reversible, which means that you will find configuration so xe on the edges strictly positive, such that the omega of ij, the probability to go from I to j, is xij over xi. So where xi is the sum for j adjacent to I of xij. So here, let me insist that so xij is equal to xji, because the edges E are non-oriented in that second version, in that reversible version. Okay, so that's the definition of partial exchangeability and its consequence, that you have a random walk in random environment. And let me now show that the edge reinforced random walk is partially exchangeable. So actually, again, I will do more than that because I want to find the limit measure. So I will compute the probability of the annealed probability of a path, and I will put it in a nice form. So you will see what I mean by that. So, again, so let P, so I prefer actually the exponent for the A and I0. So it should be PA I0, be the law of the edge reinforced random walk with initial weights A and starting from I0. And so here let's show that the edge reinforced random walk is partially exchangeable, and let's show that formula. So again, so here you need to think a little bit more than for the earned case. So first look at, so when you compute that probability of a certain path, let's look first at the numerator, because the numerator is the simple part. So simplest part. So first you start, let's say when you cross an edge E, the first term you get on the numerator is AE. When you cross it a second time, you get AE plus 1. When you cross it an nth time, it's AE plus n minus 1. So it's kind of obvious that the term on the numerator should be the product for E in E of AE and E. So remember that AE and E here is the same notation that I introduced for the Pólya urn, so which is here. So A up the product of A up to A plus n minus 1. So now what do you have on the denominator? So it's a little bit more complicated. So first look at the site you start from. So the site you start from is special because the first term you'll have on the denominator will be AI. So again, so AI here has the same definition, that is the same or throughout the mini-course. So it should be the sum for J adjacent to I of AIJ. So the first term you should have is AI0 and the denominator for the vertex I0. So now what is the next term you should have? So every time you visit a vertex, you have to visit twice corresponding edges. So you have to visit one edge when you go away, and you have to visit one edge again, so maybe another one when you come back. So you visit twice, so you have something like AI0, AI0 plus 2, etc., multiplied by up to AI0 plus 2 ni0 minus n, so vi0 minus 1. So sorry, ai0 plus 2 open parenthesis ni0 minus 1, vi0 minus 1. And now what happens for the other vertices? So for the other vertices, when you come to those vertices, you will have visited once the corresponding so one edge to arrive there. So that's why you will start, instead of starting with AI, you will start with AI plus 1 if you are, so if I is not I0. So obviously, so now what I'm rewriting that process of A plus 2, etc., using the same notation. So that's why I have the power of 2 and that expression. And now, so it's a nice computation to show that actually you can write it in kind of elegant way as gamma of xn z of n. So here z of n is this is I should write z of n minus a, because z of n is basically the numbers. No, let me see. No, it's fine. No, it's this. So it should be gamma of xn z of n divided by gamma of I0a. And now, so my definition here of gamma of I0 alpha is the product for I in V of gamma of 1/2 of alpha I plus 1 minus the Dirac at I0 multiplied by 2 to the alpha I minus delta I0 of I divided by 2. The whole thing divided by the product of alpha E. So I really encourage you to do that computation, which goes from first, the second part to the third part. So you'll see that actually it comes very naturally. And so one interesting thing, so I'm anticipating the future, is that this gamma will be actually somehow the greatest part of the normalizing constant that you will have on that law. So it actually comes naturally, but it really comes naturally from that computation of the annealed path, the probability of the path annealed. So okay, so now let's take again a statistical view. So the statistical view is that you want to do some statistics on reversible Markov chain. So you have a reversible Markov chain with an unknown random vector x, which gives the probability transitions. So the probability to go from I to j will be xi j over xi. So the question is that you don't know x, so how do you estimate x? So again, the Bayesian approach is to say, okay, we assume that we have a certain prior distribution of on x, so whatever it is. So we assume there is a distribution, and now here, so note that here, if that distribution is exactly the distribution of the limit. So the limit proportions, actually the law will be the law of the edge reinforced random walk. And so again, so now you can say, but so here you can do Bayesian statistics that once you've done n steps, then the new law will be P xn Zn of E. And so, sorry, I should write ZE of n, so I change the notation. So because you start a new process at a new site with a new number of visits. And again, so that means that the prior and the posterior are conjugate priors. And so Diaconis and Freedman in 2006 proved that actually, so that number of visits, crossings of E, so the vector of number of crossings of E for all E is a minimal sufficient statistics. So the same with the same notion that I introduced beforehand. And they also provided a method for the simulation of the posterior. So now, okay, so now how can we find the limit measure? So again, you can do the same. So you can do again Bayesian statistics. So you say, assume that law here has so of the environment X, you know that there is an underlying environment X. So assume that the law of that environment has integrable smooth density phi A I0 on the simplex. And so you can always assume that you are on the simplex, that sum of XC is equal to 1 by renormalizing. And then you compute the probability starting from A I0 of the limit capital X, so the limit environment capital X between X and X plus dx, knowing a certain path, from I0 to IN, which so I will also call IN J0. And so that probability you can write as phi A. So again, so let's start by the denominator. So the denominator we already computed. So that's the probability of A. So starting from A I0 configuration of the path. So we already computed. This is simply gamma of I0A divided by gamma of J0 alpha, where alpha is the new weights configuration. So now of the numerator, it will be phi A I0 of x dx, because so that's the probability that your x is between x and x plus dx. And knowing that it's x, what is the probability to do a path? So this is now the quench probability of a path. So that would be the probability, the product for E in E of xe to the power of NE, where NE is the number of crossings of E, divided by the product for vertices I of xi to the power of VI minus the Dirac at J0 of I. So the reason why you have that is that the last point you visit, so you don't have to count for the numerator because you don't leave from there. So then again, so once you are in J0, so then you get again by the same argument, you get that formula that phi alpha J0 is equal to phi A I0 multiplied by that quench probability here, divided by gamma of I0A over gamma of J0 alpha. So you get that formula. So now the argument to conclude for what the limit law is will be basically the same as for the Pólya urn. So when the time is very large, so the NEs are very large, so that product in the middle, that quotient of products in the middle, it will be concentrated. It will be some almost Gaussian, and it will be concentrated around the proportions of visits of edges. So that's what we are going to prove at the beginning of next lecture. And so here I'm so just to write what the limit measure will be. So this will be so in summary, what do we have? So the first part, so that the fact that the proportion of visits to edges converges almost surely to a random vector, so it simply follows from exchangeability. Now, conditionally on that limit, you have a reversible Markov chain. Again, it's a consequence of exchangeability. And now, so you see that you recognize here the product, which is which corresponds almost, to the product here, the product in the middle here, a product of xe to the ae minus 1 over product of xi to the ai over 2. And actually, you even see here the square root of xi0, which corresponds to exactly this delta J0 of I that you have here. So you recognize that part. The gamma I0 alpha we already defined. It was defined when we computed the anneal probability of a path. Now the C, it will be so it will correspond to that Gaussian in computation of Gaussian integral, and d of y. So this is a determinant but also by matrix 3 theorem. You can write it as a sum on spanning trees of the product over the spanning trees of the YEs. So we'll explain a little bit more at the beginning of next lecture how we obtain that square root of d of x term. So I think I will stop here. Thank you for your attention. So please ask me questions now if you have some.
Thank you. Yes. So I think anyone should be able to unmute for questions. And one thing for this partial exchangeability, this works on either directed or undirected graphs, right?
Yeah, so in the directed graph, then the exchangeability is that the probability of doing the path only depends on numbers of crossings of directed edges, right?
Yeah.
So now if you do a undirected graph, so if you take the reversible, okay, let me write here. So if you take the reversible version of exchangeability, which is, no, it's before, so then you would have a probability of a patch which depends on the number of crossings of undirected edges. Okay? But you could also take a undirected graph and use only the the non-reversible partial exchangeability here. So you have so you could choose a process which itself is not reversible.
Sorry, cannot you comment the formula for the measure which on the previous slide?
Yes.
There was in nominator something like AE, BE. What is this? It's functional. What is it? What is it?
Where? So for the Pólya urn or for the
nominator AE and E? What is it?
So I don't see where it is.
Well, yes, here. No. Before.
Here.
No, just formula for measure. There was in nominator was a bracket AE and E. What is it?
So it's defined at the beginning. So it is a product. So AN is a product of A plus 1 after A plus N minus 1.
Okay, I understand.
Yeah, I defined it for the Pólya urn.
Thank you.
So question? Regarding that same formula, what is the BI?
Before we continue, let me just, and before people start leave, let me just mention, so tomorrow, 2 hours before the talk, there is also a review session and a discussion with Pierre, and otherwise the next talk is tomorrow at the same time, and the third talk will be on Thursday. And they will also stop now the recording, and the live stream, but we can continue with questions. So go ahead.
Yeah, sorry.